teaching. You can follow the directions. It shouldn't. It should be how the image shows it. So what is the total displacement? So area under the curve. So this has a 2-second base. This has a 4 meter per second height. This has a 2-second base. This has a 4 meter per second. And this has 4 seconds. So this area is what? 4 meters. This area is, and this area is 8 meters. So the total displacement, I would actually draw the shapes and showing your work, plus and this is 8. So 8 plus 8 is 16. 16 plus 4, this gives you 20 meters. So how would the acceleration time graph look? Are you writing in pen? I'd write in pencil, because I want to see you do it first, and then in case you're wrong. Especially on this graph homework, because I don't want to see this. I don't want to see, oh wait, I should have drawn that too. No. It should have been a straight line. Oh, it goes down from this. I don't want to see that. Because on your homework, you're actually going to be drawing on graphs. So from 0 to 2 would be what? Squared. So you're just translating slopes. It's accelerating at 2. Yeah. So how would I draw it? Would I go up to 2? Okay, yeah. So it looks like that. You don't have to draw these lines connecting it. It's a problem of whenever I'm drawing these that they have to be connected in my drawing program. But technically, there is no vertical line. You can draw this imaginary vertical line if you want. It doesn't matter. But it's technically not really there. And then between 4 and 6, it'll go back down to 0, because the acceleration is 0. And then for the last 4 seconds, -1 meter per second squared. So this is the acceleration. So here we have an acceleration time graph. So it says draw the velocity time graph assuming the car is initially at rest. So when you're going in the other direction, if I'm going from acceleration to velocity, you don't know, because acceleration is just change in velocity. So this just only tells you how your velocity is changing. It doesn't tell you what your velocity is. It only tells you what it's changed by. So this tells you that your velocity is changing by 1. We need to know initial value. Here it tells you we're going to start at 0. And then this is going to tell you how this 0 is going to change over time. So how would it change? What would be the first thing? So it would be, so this is 1, so it's increasing by 1, so it'll go 1 meter per second for 2 seconds. Then between 2 and 4 seconds, the acceleration is 0, so velocity doesn't change, it'll stay constant. Between 4 and 6, our acceleration is -2. So we're going to go down by 2 and over by 1, go down by 2, over by 1 for 2 seconds. No, so this value is 1 meter per second squared. So you're going to go up by 1, over by 1. So up by 1, over by 1, up by 1, over by 1, and you repeat that until you reach 10 seconds. Then it asks, what is the total displacement of the car? So displacement of the car can be done by finding the area under velocity time graph. So displacement can be done by finding area under a velocity time graph. I would like to note one thing, I haven't specified it. The area under an acceleration tells you your total change in velocity. So the area right here is 2. So that means we went up by 2 meters per second. The area here is 0, so we changed by 0. The area here is -4, so we start at 2, we'll go down to -4, and this goes to 6, so we'll go down by 4 over. So you can look at area under this. So the area under this curve is 4. That tells us that our total change will be 4 over. Or I would recommend that you just look at this acceleration and be like, it's 1 meter per second. So we're adding 1 every single second. That's probably better than doing area. So we can draw our shapes. So what'd you get as the total area? What? Or the whole thing, I mean. Yeah, so negative, so the height is -2 meters. -2 meters per second. What meter? Mm-mm. So a half times 2 times 2, just 2 meters. 2 times 2, 4 meters. A half times 2 times 1, just 1 meter. A half times -2 times 3, so that would just be -3 meters. And a half times 2 times 2, 2 meters. So the base here is 3, and the height is -2. So adding that all up should be 11 meters. Then it asks you what the total distance will be. Did I do that right? 2 plus 4 plus 1 plus -3 plus 2. I made a mistake, probably 11 meters. Let's see, point. 2 times 2, 0.5 times 2 plus 1, 0.5 times 3. Yeah, I made a mistake. This should have been 6 meters. Two plus 4 is 6, 7, 8, 9. 9 minus 3 is 6. And then what would it be for total distance? So remember, distance doesn't have a direction, so we don't care about plus or negative. We don't care about positive or negative. We treat them all as positive. So it'd just be 2 plus 4 plus 1, and then we add the 3. That's the only difference between distance and displacement. So you get 12 meters. So here we're given a displacement time curve. And it says draw the velocity time graph of a traveling car. So we need to draw velocity. Velocity is going to be equal to the slope of displacement. So we need to be looking at slope. So going from distance to velocity, because velocity is distance over time, so we do distance over time. So this is a slope of 1. So we draw 1 for the first line segment. This has a slope of 0. So we draw 0 here. This has a slope of 1, so we draw slope 1. This has a slope of -2. This has a slope of a half. And then this has a slope of 2. So this would be the velocity time graph. Note, if you wanted to, you can draw these connecting things. Because that's how it's going to look like. Because I can't draw it without adding these lines into it. But the main thing is these values. This is actually the only part of the graph that's accurate. The reason why is because you can't have more than one speed at a given time. So if you have a vertical line, that tells you have all these values. The vertical line isn't really there. So using the velocity time graph, calculate the change in displacement. Well, this one's easy. We have just rectangles. So see if you can calculate the change in displacement using the graph. You get an answer? What is it? So we have, you can almost just count the squares. So 1, 2, 3, 4. This little half is actually 1, so it's a half a square plus a half a square. Then 2, and then the bottom one would be -4. So add them together. Note, if you are given a displacement time graph, so we calculated the change in displacement. What is change in displacement? So delta x is our change in placement is equal to xf minus xi. So final minus initial. So let's look. Our final was 3 meters, and our initial was 0 meters. That's your xi. This is our xf. So if we're given a displacement time graph, we could just plug in final minus initial, and we get 3 meters. You can also tell that this is a homework I didn't use last year because I still have x naught. X naught is the same thing as xi. It's just so this technically a lot of people use xt and x naught. This is your displacement at time t, and this is your displacement at time equals 0. And we began initially at time equals 0, and some time later t. So problem 4, it wanted you to show all the work. But just looking at the graph, can you immediately tell what the total displacement is? What is it? 0. Because we have it mirrored so that we have this shape, and then we have a corresponding shape here. And then we have a shape here, and then a corresponding shape here. So you should see that at 0 meters, we can calculate this out. So this is an area of 1, 2, 3, 4, 5, 6 meters. This has 1 plus a half and another half, so that would be 2 meters. And this would have be negative 2 meters and negative 6 meters. Then ask you to draw the displacement graph from it. So this is a ball shot out of a cannon. So assume that the initial cannonball is at rest at 0. So during the first 3 seconds, or displacement is changing by 2 meters every second. So we go up by 2 over by 1, up by 2 over by 1, up by 2 over by 1. And this would be a straight line. Now our velocity is changing. Hello? Yes. Alright, I'm going to send Nicole with them. Bye. Nicole, would you send the transcripts up to the office? He's right here. So now we have to draw a parabola because our velocity is changing. How good are you at drawing parabolas? So what we can do is the area under this curve is going to be your change in displacement, right? So if I draw the area between 3 and 4 seconds, so this is 1.5, right? So I know that between 3 and 4 seconds, I go 1.5 up right here. Right here, between 4 and 5, is a half. So I know between 4 and 5, I'm going to add a half. So I'm at 7.5 and a half. It'll go right here. Here is would be a negative half. So I would go back down by half. And then between looking at this segment right here is 1.5. So for between 6 and 7, I would go down 1.5 to right here. And then between 7 and 10, it's just subtracting by 1. So, this is how I would recommend doing it. Because you probably couldn't have drawn the most important thing is this top point. And so you can break this up into smaller and smaller graphs. So if you want, this is good enough. You can now, once I fill in the rest of this, nope, it should go right here, and that should go right here. So that, and then there should be a parabola right here. Here you can sketch a parabola better now. If you wanted to be more accurate, we can divide this up into a half a second. So this has an area of half. So looking at the shape, we have a small triangle above it, and a small square. And this goes too far. We have a half right here. This height is 1. This height would be a half, and then this would be a half. We added that all up. 0.5 times 1 plus 0.5 times 0.5 plus a half times a half times a half. I get that between 3 and 3.5 seconds, the area should be 0.875. So between 3.5, I should go up about to right here. But again, that's unnecessary. As long as you're within a second resolution, that's pretty fine. And here you can just round the shape. And that's close enough. The important part of doing this, though, was figuring out what was the max distance. Because now we can see that the farthest they got from the start, or if this was a cannon you're shooting up in the air, you can see that the cannonball reached the height of 8 meters. So you launched it straight up into the air, it reached the height of 8 meters, and then began falling back down. So we can take the velocities and get this parabola shape with these lines right here. Also, so using the distance time graph, calculate the total displacement of the ball. To do this, we have a parabola. And do you know how to find the area of a parabola? Neither do I. I mean, I do using calculus, but I don't know how to do the area using algebra. What you can do is do what I did earlier. We're just going to estimate it. So let's draw some shapes. So we know this area. This is 1, 2, 3, 4, 5, 6, 7, 8, 8.5. No. Let me stop counting and actually calculate it. 9, exactly 9 meters. This would be 9 meters by symmetry. This would be 24 meters. So do you notice I'm making a mistake? This is actually not right. I wanted to demonstrate how you could do area under a parabola. We can represent this by a triangle. But what is total displacement equal to? Yes. Because it starts at xi and it goes to xf, also being 0. So the displacement is 0. So a car at rest begins accelerating at 10 meters per second squared for 2 seconds. The car then maintains its current velocity for 4 seconds, so we have a word problem. So a car at rest begins accelerating at 10 meters per second for 2 seconds. So drawing the acceleration curve, it's 10 meters for 2 seconds, 10 meters per second. The car maintains its current velocity, so that tells you that its acceleration is 0. It does that for 4 seconds, so between 2 and 6. After which it begins accelerating at 20. So come up to 20. It does that for 2 seconds. And then spotting a cop, they realize the car's velocity is well over 130 miles an hour. So the driver panics and begins decelerating at negative 25 meters per second for 2 seconds. So assuming the car is at rest, doing a velocity time graph, we'll start at 0. This tells us we're changing by 10. So we go up by 10 for 2 seconds. Then we maintain that speed for 6 seconds. Then we accelerate at 20 meters per second squared for 2 seconds. So we'll go up by 20, then go up by 20 again. And then we're going to slow down by 25 for 2 seconds. So over 2 seconds, we'll decrease to 50, by 50. So we'll go, I can just look at it. We're starting at 60. We'll go down by 50 over 2 seconds. So it should meet here at the halfway point. Now we've drawn our graph, we need to figure out displacement by doing triangles. Note here we're not going to have a pretty triangle because this is not quite a triangle and it's not quite a square. What we'd have to do is draw a line like this. There's multiple ways you can break the shape up. This is the first one I look at. And then I draw it like this, like that. There's probably better ways you could have broken this up, but I want nice, neat triangles and squares, or rectangles, I mean. So a half times 2 times 1. This is just, or no, this is 10. So make sure you pay attention to the numbers. So this is 20 times a half, so that'll be 10 times 1. So this will be 10 meters. 20 times 4, 80 meters. So this goes from 20 to 60, so 40. Half of 40 is 20. 20 times 2, so that's 40 meters. This is 50. Half of 50 is 25. 25 times 2 is, so this is 50 meters. 10 times 4 is 40 meters. 2 times 20, 2 times 10 is 20 meters. I believe I did it right. Trying to rush because of both othering. I get answer 240 meters. Let me double check. So 20 times 2, 20 times 4, 2 times it is 240. Seems pretty simple, right? Let me check. Probably should have gave out homework 3 already, because I'm not covering anything new. I'll do that tomorrow.